Welcome back. We are continuing with the search for perfection in physical sciences. Teachers, learners, this is the platform. Let's continue to engage. This time around, let's focus on chemical equilibrium, which is normally question number 6 in a normal question paper. We've got the recent question paper here. Let's just go through it. Ammonia is produced by pouring nitrogen gas and hydrogen gas in an empty container and allowed to react in a closed container according to the following balance equation. The graph of the rate of forward and reverse reactions is indicated below. I think the missing part is just to show that the dotted line is forward and then the solid one is a reverse. But we see that. Okay, anyway, the first question, that is 6.1.1, normally definition, yes. Define the term chemical equilibrium. Remember, chemical equilibrium, there are two different definitions. The first one, you can use the rates. So you can just say the forward direction when the forward reaction rate is equal to the reverse reaction rate. So that's when you define in terms of rate, or you can define in terms of concentration to say it's when the concentrations of the reactants and products remains the same, remain unchanged, remain constant. That is the definition of chemical equilibrium. The next question, they say identify the change made at time B. You look at the time B, you can see that we know that in this case there are two factors that can cause this, but there's one factor that can do this in all equilibrium. In all equilibrium, catalysts can do that, but in selective equilibrium, like the ones whereby a number of moles of the reactants and products remains, they are the same, they are equal, then also increase in pressure can do that. But in all equilibrium, catalyst addition can do that. Okay, then in this case now, because moles on the left and the right are not equal, therefore at B will be catalyst was added. Catalyst was added, or addition of a catalyst was added to the reaction vessel. 6.1.3a. They say there was a temperature change at time C while the pressure was kept constant. We see now when you look at time C, something was decreased. Why? Because the rate of the reverse and forward, they are decreasing. And that what can decrease the rate is when something was decreased, either pressure, temperature, or concentration. In this case, now let's hear the question. How did the temperature change? If the temperature was changed at this one, temperature then was decreased because the rate drops. The temperature change, right, only increase or decrease, then we'll just say decreased. Then number B, is the forward direction exothermic or endothermic? Lastly, now when you decrease temperature, according to this one, the dotted line, which is the forward direction, is higher than the bold one. Therefore, the rate of the forward is higher than the reverse. Therefore, it means that forward direction was favored. Therefore, it means that forward direction is favored by decreasing temperature is an exothermic. So forward direction will be exothermic. And then number C, they say use Le Chatelier's principle now to explain the answer that you provided above. Therefore, we just say, okay, fine. Two principles there. Decrease in temperature, first bullet. Decrease in temperature in terms of principle, decrease in temperature favors an exothermic reaction. Exothermic reaction, you get 1 mark for stating that principle, very important. The second one, now after that one happened, which reaction is favored? According to this one, forward reaction was favored. Forward reaction is favored, or you can just even say the rate of the forward reaction, rate of forward reaction is higher than or greater, than the rate of the reverse or reverse reaction rate of a reverse reaction. So I think it's understood. Fine. We move to the next part of this question. They say to us 6.2. That's 6.2. They're saying to us decomposition reaction of nitrosyl chloride is represented below. There's a case at a temperature of 50 degrees. 4 moles of NaOCl is placed in a 2 decimeter cube container. At equilibrium, it was found that 0.9 mole per dm cube of NO was formed. Okay, now the first question, they say 6.2.1, define the term reversible reaction. Therefore, we know that a reversible reaction is reversible when products can be converted back to reactants. If products can be converted back to reactants, we say that the reaction is reversible. Thank you. We go to the last question here, which is the longer one, 7 marks. They say to us here, calculate the Kc at 50 degrees Celsius. Remember, Kc, when we calculate Kc, the temperature has to remain the same, because if you change the temperature, Kc value will change. That's why the temperature is kept constant, so that the Kc won't change, because temperature change is the only factor that change the value of Kc. Fine, we are in 6.2.2. We're calculating Kc value. What we do, 7 marks, we just have to draw the table. Therefore, we copy the reaction, 2NOCl, reversible with 2NO plus Cl2. Fine. What we do, remember, we have to draw 5 lines below this one. That's the best method. Draw 5 lines below the equation. 5, 2, 3, 4, and then 5. Create a column for each substance. Each and every substance must have its own column. On the left hand side, just create a space just to tell us which method I'm using. Remember, there are 2 methods in this case. I can use the mole method or the concentration method. The well-known one is the mole method. Just say initial mole, Ni, change mole. This one, remember, it's about the reactants and products, or it will be using also, very important, the ratio, that is 2:2:1 in this case. Some cases you just write used or produced is fine. then the number of moles at equilibrium, or the moles at the end, and then the concentration at equilibrium. That's the best method. So now, according to the given information here, we are starting with 4 moles of NOCl. We just write 4 moles. Nothing is said about the products. We assume that we start from 0. At equilibrium, what is given? They are telling us that when equilibrium is reached, 0.9 mole per dm cube of NO was formed. Now at equilibrium, concentration, we're given concentration at equilibrium of NO is 0.9. Very important for us to work this one. We need to find what is the volume of the container. According to this one, the volume of the container is 2 decimeter cube. Therefore, if the volume equals to 2 decimeter cube, which means that now we know from here to here we divide by volume. If you move from concentration to volume to number of moles, we are going to use now, remember the number of mole equals to CV. A very important formula. So multiply the concentrate by volume. This one multiplied by 2, it will be 1.8. And now if you started with 0 and finish with 1.8, therefore how much was produced? It will be positive. This 1.8, fine. Then I can just quickly know that this positive, negative, fine. No problem. Everything will start from this one. So I can change the color if you allow me. Fine. You will find this one. Use the red color, which is visible. Everything will be revolving around the 1.8. Use the ratio 2:2. This will be 1.8. 2:1. Therefore, half of it is 0.9. This one will also be 0.9. Divide by 2 becomes 0.45. No problem. In this case, if I started with 4 and I now subtract 1.8, will be around 3.2. So it's fine. Is it 3.2? No, not 2.2. Fine, 2.2. Then now 2.2 divided by 2. Remember the volume is 2. Therefore, it will be 1.1. Quickly, you finish with the table. Remember in the table, the principal normally is 4 marks. So ratio is 1 mark. 1 mark for the ratio, usage of the ratio. 1 mark for the change in the products. 1 mark for the change in the reactants. 1 mark for the dividing by volume here. So which will be the case. No problem. You get 4 marks for saying that. Now let's go to the next one. They say calculate the Kc. Kc, you write now the Kc expression, the products over reactants. Product is NO because it's now 2. Then the coefficient becomes the exponent, multiply by Cl2, and then divide by the reactant is NOCl. Then also squared. Then what you're going to get in this case, you will find now that the products will be 0.9 multiplied by 0.45, 0.9 squared multiplied by 0.45. Yes, and then from here divide by 1.1 squared. That is the case. And then from here you can just consult your calculator. Let me just see if I can get the calculator here and then work it out and see. If I use my calculator, the answer gives me 0.33. So the final answer will give me 0.33. That's how you do it. If you want to do it alternatively, just quickly just to show you that there are many ways to do this one, but the normal way that everyone uses is this method of using the moles. Others can use the concentration. You will find that now concentration is shorter. You will be having 2 NOCl, and then have your 2NO, and then have your Cl2, and then with concentration we draw only 4 lines, no longer 5. 1, 2, 3, and then 4. So would be 4, and then this side with concentration, it will be now the initial concentration, the change concentration, and the concentration at equilibrium. Now, because we are given 4 moles initially, then we need to change it to concentration. So 4 moles divided by 2, therefore it means that the initial concentration of NaCl will be 2. And then this one becomes 0, 0, no problem. And at equilibrium we are given the concentration of NO, which is 0.9. Therefore we'll write it here to say this is 0.9. Therefore if you start with this one and produce 0.9, we'll get to 0.9 here, and this will still be according to the ratio 0.45, and this will be 0.45. So ratio 2:2, 0.9 is to 0.9. This one minus this one will get 1,1. If you look at this one, you can see that this last one is the same as this one. You see 1.1, 0.9, 0.45. 1.1, 0.9, 0.45. That is the concentration method. You don't find it in many books, so you can find it in study guides, but it's an alternative method. But the easiest one that everybody knows, obviously, is this one of moles. Very easy to do, and start with this one. So they don't start with ratio stuff here, so it will be putting too many data on the table, then it will end up confusing you. Leave the ratio with the balance equation and start with the initial moles. I think that's the best method. That will never go wrong if you use it accordingly. I hope we know how to deal with this KC stuff here, especially this one, which is just a straightforward from top down. So we'll also try to check questions where KC is given, and then so that we work from bottom up. Until we meet in the next session, I think don't forget to subscribe, and then also share the word with your fellow students about the knowledge that is gained through these videos. We are very thankful of the information, the feedback that we get, that learners are getting help. We appreciate, and we just say keep on supporting, and then keep on also listening to this. You will never go wrong. Thanks a lot. Until we meet in the next session. Bye.